Hello everyone. In this video, I will demonstrate why to pre-screen the data before you perform any multivariate data analysis. And I will be referring to SS chapter 3 from this book here. It's a very good book on multivariate data analysis. So let's get started. One question that always comes to our mind is why to screen data prior to conducting multivariate data analysis. So there are, you can say, four reasons. One is the accuracy of the data. The data on which you are performing statistical analysis should be as accurate as possible, because if the data is not accurate, then all the statistical analysis you're going to perform will produce erroneous results. So you need to understand that garbage in is going to be garbage out. So first thing first, you always need to check the quality of the data. Second thing, you have to see if there are any missing values. I guess the more important question is the pattern of the missing values. So the values that are missing should be completely missing at random, because if there is a pattern, then the results may not be generalizable. For example, let's say you have a variable called income on which you are collecting the data. So the wealthy people are not responding to that question, but all the sort of less wealthy people are responding. So that means there is a pattern in the data, and the results may not be generalizable. So that's another reason you have to thoroughly analyze the missing values. The third thing is dealing with the outliers. Now, as you may know, most of the statistical analysis are kind of very sensitive to outliers. Specifically, wherever you assume normality and linearity, outliers could have profound impact, such as multiple regression. So one must deal with outliers either by deleting those cases or maybe transforming the variable. Then the fourth one is to assess the adequacy of fit between the data and various assumptions of the procedures. So we always assume normality, linearity, and heteroscedasticity. So we need to make sure that our data is both univariate and multivariate, normal and linear and homoscedastic, or that assumption of homogeneity or variance is satisfied. So with this brief introduction, let's get to the example. Let's say we are interested in investigating income. That's a variable name. Differences between individuals who are either satisfied or not satisfied with their job. Sat job 2 is the name of the variable. So this is a typical case of a very simple ANOVA, where you have one dependent variable, which is ratio scale, and one independent variable, job satisfaction, which has two categories. So it's categorical. So let's go ahead and analyze the data and go through all these 4 points here. So I'm going to go and open the SPSS here. So that's the data we have here. Career.a.sav. I would like to go to the variable view here. We have a lot of variables here, but we are interested in job satisfaction, which is kind of a binary here. You can see here, very satisfied is 1, not very satisfied is 2, and our income 91. Okay, so this one has already missing values, but we need to deal with that one. But if you see the values here, it has sort of ordinal values. Okay, so it has a lot of categories, more than almost, it has 21 categories. So it is treated, in fact, as a ratio scale. So one thing you have to keep in mind that is, even for our Likert scale or data where we ask the respondent to choose one of the 5 categories, we treat that as a ratio scale data. So here we have more than 20 categories. So this could be very well treated as ratio scale data. Okay, so that's the one thing we have to keep in mind. Now, if you see the values here, you'll see that 22 category is refused, 98, 99 are NA. So these 3 are not actually the income categories, and they should be treated as a missing value. So the first thing we're gonna do here is to recode these values as a system missing. Okay, so we're gonna do that here. So what we're gonna do here is I will go to transform recode into different variable, and there we're gonna choose our income. This is the one, our income 91, and we're gonna give it a name, our income 2. Then we're gonna say that a range to highest, so anything above 22 and up should be treated as system missing. Okay, all other values should be copied as is. Okay, and continue that one. So we're gonna say okay here. So this is gonna go ahead and create a variable here. So if you go all the way to the end, you should be able to see our income 2. Okay, I guess this should not be. I'm going to delete this one. Okay, so we just created our income 2 here, and where we have those values here, we treated that as a missing value. So category of 22, 98, 99. Okay, so now we have taken care of the first point as such, the accuracy of the data. Okay, now looks like our data is valid here. We're going to move on and do what we call missing value analysis. Now, when you do the missing value analysis, you have to do it 2 ways. One is the case wise, where if any case has a missing value, that case will be ignored. So we have to sort of do complete case analysis, where a case has all the value for all the variable. So when you do the case wise analysis, we need to see that how many cases are there where you have some value of the variable of interest are missing. And secondly, we have to also do the variable wise analysis, where we have to see per variable how much data is missing. So when you do the variable wise analysis, in a way you're looking at a column and see how many values are there. And when you're doing a case wise analysis, basically you're looking at the rows, but if a row has any one cell missing, that complete case is denoted as a case with a missing value and is ignored. Okay, now another thing you have to keep in mind that if the number of cases having some missing value is less than 5%, you can just delete those cases. In SPSS, we perform list-wise analysis, where any case that has a missing value is ignored and only complete case analysis is done. If the number of cases missing are above 5% but below 15%, again it is above 5% and below 15%, 15%, then you can do some sort of imputation. So when you're doing the imputation, if you are dealing with a numeric variable, then the most common imputation method is the mean substitution. And when you're doing or when you're dealing with the categorical variable, then the most frequently used method is substitute with the most frequently happening categorical value for that variable. And it's always good to create dummy variable to keep track of where the imputation was done. So for example, if you have a categorical variable called income, and that has 10% missing values, so what we're going to do is we're going to impute those 10% of the values, but we will also create a additional dummy variable where all those 10% of the value will have a value of 1, and the rest of the 90% where imputation was not done will have a value of 0. So this kind of captures the missing value information, and when you run the analysis, probably you can see if there is any pattern there, or does the people who are mentioning the income are more important compared to the people who are not matching the income. So that's something to keep in mind. And if the missing values are more than 15%, then basically you should consider dropping those variables. Okay, so that is another thing you can think of doing it. So let's go ahead and do it here. So what we're going to do is we're going to go to Analyze, Descriptive Statistics, Explore, and we're going to put in both of our variables. So job satisfaction, I guess that job satisfaction, yeah, that's nominal, that's what we're dealing with. And the one we just created here are income 2 here. So both in the dependent list. Stats, we just want descriptive statistics here right now. We don't want any plot, we're not interested in any plot here, so I will just click on statistics here and say okay. So what he's going to do is going to take these two as one case. One case has 2 cells or 2 values, one for job satisfaction and one for job income. So if any of these 2 cell has a missing value, that case will be denoted as a case with a missing value. So here we just need to see the first column. In all, we have 710 records, out of which 37 records or 37 cases have some sort of missing value. Now this missing value could be either in job satisfaction or our income too. We don't know, but we only know is we have only 747 cases that has complete values and 37 cases that have some missing value in there. So so this is only 5%. So since it's only 5%, what we're gonna do is we're gonna do list-wise analysis where all these cases will be ignored by default by the SPSS. So we don't need to worry about missing values anymore here. Okay. Now we are done with the case-wise. So it's always good to see the variable-wise analysis as well, where we see each variable, how much missing value is there. So for that, what we have to do is we have to go to Analyze, Report, Case Summaries, and I'm going to put our income and job satisfaction here. Stats, just number of cases I'm interested in. Deselect this option here. Option, we don't need to worry about any details here. Say okay here. So basically it's gonna give you variable bias case summary. So in other words, job satisfaction does not have any missing values. So we see all 747 columns or cells have values, but income variable has only 710 values out of 747, so 5% missing. So when we did the complete case up here, all these 37 missing values were coming from basically only one variable, which is our income 2. So basically, in this case, we only have 2, but when you're doing a factor analysis where you're dealing with 20 or 30 um, interval scale data, then you have to see all these missing values and see if you see any pattern there. Most of the time, this is not maybe as robust technique to scan for missing values to see if the data is missing completely at random, but obviously it is going to give you some good hunch to continue with your analysis. So you have to see that there is no pattern in the missing data again, and the data is missing completely at random. So it's always good to do both of this analysis. Okay. So we already decided to sort of delete those cases here. So we are done with the second option here, missing values. Now we're gonna start dealing with outliers. Now, when you're doing the outlier analysis, since we have job category that has 2 categories here, we have to sort of see the outlier in each group. So we're going to form 2 groups here. One group will be people who are very satisfied, the other will be people who are not very satisfied. And we want, first of all, to have more or less an even split of data between the 2 categories. Because if the split is not even or is highly uneven, like one category has 90% of the data and other category has only 10% of the data, then it's not worth continuing with the analysis, and you should drop such a categorical variable because the statistical analysis will not be accurate, and you might misinterpret the results. So that's something you have to keep in mind. So we're gonna go ahead and start doing the analysis. The outlier analysis is basically done using outlier analysis, and let's go ahead and do that here. So what we're gonna do is analyze, explore again. So this is going to be the same here, but first of all, our income should not be nominal. We have to convert that into ratio scale. So I'm going to go here and I'll say this is a ratio scale data. Okay. And then I'm going to go to again descriptive statistics, explore here. So I guess it's still showing me that thing here. So I'm going to save this one. Hopefully that will help me with that one. Still showing me that one, but we're just not going to ignore. We're just going to ignore that one here right now. But just keep in mind that that's interval scale data. Okay. So in the statistics, we have to click for outliers. Okay, this is gonna help us identify the extreme values here. Okay, and we want both statistics and plots. In the plots, we want a box plot. It's always good to see the box plot. We also want the stem and leaf plot here. So that should be the option we should be choosing here. Continue here and say okay here. So we see that one category has 313 records and the other category has 387 records. So it's like fairly, I would say, even. It's not highly uneven. So there is no point of deleting this job satisfaction variable. So we're gonna go ahead and continue our analysis here. So again, this is not that severe that we should be worried about. So that's the first thing. Then we're gonna go to the extreme value here. Okay. Now this extreme value shows you the highest 5 values and lowest 5 values in each category. So these may not be necessarily outliers, but these are the highest and the lowest value here. The box plot is gonna give us specific details here. Box plot gives us the case numbers, which are outliers. These are all outliers. And stem and leaf plots, it gives you more information. It tells you straight away that there are 11 cases where you have extreme values less than equal to 0. In case of very satisfied, in case of not very satisfied, you have 22 extreme values where you have values of less than equal to 3. Yeah. So because number of outliers are present as such here, what you can do is either you can delete those records with the outlier values, or you can transform them in some way. One of the way you can do that is the method known as winsorizing. What we can do here is we can alter the values here and change it to the one that is within the extreme tail in the accepted distribution. So this is something called winsorizing. Okay. So here what we're gonna do here is here we see that 11 has extreme values less than equal to 0, 22 have extreme value less than equal to 3. So what we're gonna do is we're gonna go ahead and change these values to 4. Okay, so anything less than equal to 3 will be changed to 4. So we are replacing sort of, this is on the positive side. So we are replacing all the extreme values with the value, with the maximum value that is a valid value in the distribution, which is number 4. This is how you do winsorizing. So all the outliers are brought back within the acceptable tail of the distribution by replacing them with the maximum allowable value in that distribution. So we're going to replace all the value less than equal to 3 with 4. So what we're going to do is we're going to go to the transform, recode into different variable, and I'm going to remove this one, or income to or income 3. And let's see, I'm going to remove this one. I'm going to say lowest through. So lowest through 3 should be changed to value of 4. Okay, and else copy the data. Okay, so we're going to continue that one here. Say okay. So this is how you take care of missing values, quality of data, and outliers. Okay. So with this one, what we're gonna do is we're gonna move next to the 4th point, where we will assess the assumptions while performing multivariate data analysis. That is normality, linearity, and homoscedasticity. Now here, since we are dealing with the univariate analysis, this is here we are basically dealing with what we call univariate analysis with the grouped data. So I'm going to say Should give a heading here, I guess. Data screening for or say simple ANOVA. So that's something we are doing it here. So while assessing the normality, what we have to do is we have to assess the normality of the dependent variable at every level of the independent variable. So what we're going to do here is we're going to divide the data again into people who are very satisfied versus people who are not very satisfied, and we're going to assess the normality in both the groups. So for example, the thing you have to keep in mind that the data has to be normal across all groups. Okay, so not only that, the data should have constant or same variances across all groups. So that's something we have to worry about here. Linearity will not be tested here because we only have one dependent variable. So linearity has to be checked among two variables. So we cannot perform that here. So let's go ahead and do the analysis here. So we're going to do here analyze descriptive stats again, explore again. So we're going to do our income here, job satisfaction here, stats. We don't want to deal with outliers anymore here. We don't want any histogram. We don't want any box plot, although that can help you see the distribution of the data. But we'll go with the histogram and normality plot test. Okay. So do here and do here. So again, these are descriptive stats here. Skewness and kurtosis is the one thing that defines whether the data is normally distributed or not. Skewness ideal value is 0. So 0 means the perfect symmetrical data. Kurtosis has also ideal value of 0. In fact, for kurtosis, for a normal distribution, the ideal value is 3, but all the statistical package subtract 3 from it and compare with the benchmark of 0. So in SPSS, both the value, if they are near 0, that tells you that data is pretty normal. These values are ranging from +1 to -1. So we want them to be near to the 0. So we do see some sort of, I would say, negative skewness in the data. The data is a little bit negatively skewed, and that could be verified using the histogram. This is the case for both very satisfied and not very satisfied here. So histogram, as you can see, is negatively skewed here, right? And not very satisfied group is also negatively skewed a little bit here. QQ plot sort of confirms the same thing. So what we're going to do is we're going to transform this data. Now there are many different types of procedures you can use to deal with the data that is not normal. More detail could be found on, I would say, page number 34 in the book. But if you have moderately negative skewed, then you have to sort of use reflection and take the square root of the data. You take the reflection, which means you find the highest value for the dependent variable in the data set in all the groups. So highest value, you're going to take that. and add it plus 1 to it and subtract all other values from this value. So in a way, you're sort of converting negative skewness into positive skewness and taking the square root. So we're going to do that here. What we're going to do is transform compute. Say I want to compute our income 4, and what we're going to do is we're going to do arithmetic here. We're going to do square root, which I don't see here, square root. Now, one thing is sure, the highest value, let's go to the case processing summary here. So maximum value here you see is 21. Maximum value here is also 21. So we know that the maximum of the two is again 21. So that will be the value we have to use for our reflection here. And we're going to add 1 to it. So we're going to subtract all the values in the data set from 22. So we're going to do transform compute variable our income 4, and here we're going to do arithmetic here, square root of, we're going to say 22 minus, we're going to subtract our income 3. Okay, say okay here. Okay, we're going to see the data has been processed here. And after that, we again gonna do and analyze the normality here. So one thing which we did not see last time, which I should have explained, is a test of normality, KS test and Shapiro-Wilk test. Kolmogorov, Smirnov, and Shapiro-Wilk test. And now they both are significant here. So this we are talking about before transforming the data. Significant means that the data is not normal. So we are rejecting the null hypothesis, which says that null hypothesis is the data is normal. Alternate hypothesis is the data is not normal. And since this is significant, we are rejecting the null hypothesis and accepting the alternate, and hence the data is not normal. So that is another reason we transform that variable. But one thing you have to keep in mind that of this test, Shapiro-Wilk test or Kolmogorov-Smirnov test, they are highly sensitive to the sample size. So if the sample size is bigger, they will always give you significant result. So this result has to be not taken too seriously as such, and one can simply move on to continue the analysis, especially if you have a large data set. Okay. Having said that, we already transformed that here, our variable here. We're gonna rerun the analysis here. Analysis, descriptive statistics, explore here. Our income is a dependent factor, is job satisfaction. All other things being same here. You're gonna change those things here. We're gonna run it, say okay here. So here we're just gonna straight go to normality test. Again, it's coming out to be significant, but if you see, I guess I should have done a transformation, which I did not do it. I should have selected the latest variables. I'm gonna rerun the analysis. We are not dealing with our income 2 anymore. We're gonna deal with our income 4. Okay, and I'm gonna say okay here. Okay. Okay. I guess earlier also when I did this analysis here, I should have taken R income 3 and did R income 2. That was my mistake. But nevertheless, you'll find more or less the same results. You can try it out yourself. But right now, after the analysis, we after the transformation, anyway, we have to use R income 4. But again, here, this one should have been R income 3. Okay. But there's not much of a difference. They are virtually the same. We are getting the same results here. So here, what we're gonna do, R income 4, we see the test of normality is again rejected. But when we compare the value of skewness and kurtosis, this has to be compared with R income 3. So let me go ahead and do that. It's not going to take that much amount of time. Remove this one, R income 3, say OK here. So this value you see 0.739 and 0.078 here. So I'm going to go here. So they have gone down considerably. They are very much near 0 in R income 4. So basically, even though the test of normality is significant, but we have considerably reduced the skewness in the data, and this is confirmed in our histogram here for both the categories and QQ plot. So since they are looking near normal, again, this normality test, they like a KS test or Shapiro-Wilks test, they are highly sensitive to the sample size. So even if they are significant, we can simply kind of ignore that here because we have a decent sample size here, and continue with our analysis. So that's how you do the normality test here. The next thing is in the list is a linearity test. Again, we just have one dependent variable, which is metric, and linearity has to be checked against at least between two variables, which we don't have. So we don't need to perform that test here. The last one is the homoscedasticity, which basically tells you that the variation in each group should be same. The variation in the dependent variable in each group must be the same. So we're gonna test that here. So what we're gonna do here is, again, we're gonna go here, analyze descriptive statistics, explore. Okay, what we're gonna do here is, since we are just want to see, we just still gonna leave their histogram normality test, but what we're gonna do is we want Levene's test as well. That test kind of test whether the data has equal variances across all groups. Okay, so data in this case is the dependent variable income that must have same variances across both the categories, very satisfied and not very satisfied. So continue that, say OK here. I'm just going to go to the test of homogeneity here. Okay, now all the p-values are sort of greater than 0.05, so they are not significant, which means that we have satisfied these assumptions of homogeneity of variance, which means that the variances are equal across all group. Variances in our income for are equal across two groups here, very satisfied and not very satisfied. So this is how you sort of go through all the data screening steps. And with that, I'm gonna stop my recording here. Thank you very much for listening. So go here, stop.